Let's begin this lecture on asteroids in 3D or 3D shape modeling of asteroids. This is going to be a condensed version of the last 8 years of my life, or 8 years of my research life, more precisely. I'm a postdoctoral researcher at the University of Edinburgh. I did my PhD at the University of Kent, and I've been in the UK last 8 years. Before that, I used to be a member of Almukantarat, and I used to be member of the council, and I used to organize camps, maybe not just like the one you're participating in right now, but they were mostly local camps where you could actually meet people. But I'm happy that despite the situation this year, this camp could still happen and that we're still able to meet, and I'm still able to participate despite being over 1,000 kilometers from you. So I'm going to be talking about asteroids in 3D. And let's begin by talking about why we study near-Earth asteroids and what we can learn from their morphology. So what you see on the screen here is a fragment of a poster from the movie Armageddon, which apparently is a really bad movie. I don't really know because I didn't see it. I just use it because I like the picture. But this is what can happen if people ignore near-Earth asteroids too much. And this is what happened, unfortunately, to dinosaurs. So near-Earth asteroids are small, relatively small solar system bodies, which can still come quite close to Earth. And they can cause, and they did cause in the past, extinction level events or catastrophic events. Maybe not at the level that that lead to the eventual demise of dinosaurs, but they can be quite they can be quite dangerous if we don't know enough about them to stop them. The methods that are depicted in the movie, from what I've heard, are a bit dubious, but fortunately we have actual space agencies that are working on methods of real asteroid deflection. And one of such missions is Hera, which is a part of a two-part international space mission. So there is a NASA spacecraft called DART, and DART is going to dart for space and reach the system of asteroid Didymos and its moon called Dimorphos. And when it's going to reach this system, it's going to smash into Dimorphos, changing its orbit around Didymos. So Didymos and Dimorphos are a bit like a model for the Sun and asteroid system. So instead of asteroid orbiting a sun, we have Dimorphos orbiting Didymos. And the spacecraft sent by NASA will change slightly the orbit of that asteroid. And later, ESA, the European Space Agency, will send mission Hera, which aim will be to characterize the impact site and the new orbit of Dimorphos around Didymos to assess how effective so-called kinetic impactors are against near-Earth asteroids. So in case we ever needed to redirect asteroid when it is coming close to Earth, we will know more or less how it works because we have a scale model of that. We're going to have a scale model of that. So this is all approved. The ESA part is approved by ESA. The NASA part is quite advanced, is very close to launch. I don't remember off the top of my head when it's launching exactly, but it's sometime next year, I think, or next 2 years. So it's going to be a thing, a big event in asteroid defense soon. So planetary defense is one reason for looking at near-Earth asteroids. Another reason for looking at near-Earth asteroids is that we are more and more convinced that they can be considered an important element of how life began on Earth. So when we look at the deuterium to hydrogen ratio in various solar system bodies, so this is the deuterium to hydrogen ratio on the y-axis here. And we have various solar system bodies in various colors on this plot. We can see that the ratio that is in Earth's ocean is marked here with the diamond and with the dark line. The ratio of hydrogen, deuterium to hydrogen in the protosolar nebula is marked here, and it's quite close to what we observe in Jupiter and Saturn, so in the gas giants. The big idea from observing some of the comets was that maybe that water came from comets, because comets, by their nature, seem to be very rich in volatile. So they seem to be very rich in material that is easy to evaporate, like, and we thought that maybe the water that is on Earth's oceans came to the young Earth from comets, but we can see that most of the known comets that have measured that ratio have it quite different to Earth's ocean. Which is actually close to Earth's ocean is the water that is found on asteroids. So looking at near-Earth asteroids, we can learn a little bit more about how this water was transported from the further parts of the solar system when it could actually stay solid ice to vicinity of Earth, where the water doesn't really condensate into ice because it's just too warm around here. So asteroids could be key to where life came from in Earth. And also near-Earth asteroids are just close to us. So in this wonderfully complex graph, I show the orbital parameters of various bodies in a solar system. The planets are marked with little dots and with their names along the bottom, if that wasn't obstructed by this thing here. Okay, so Earth is here at 1 AU, 1 astronomical unit, and then the gray dots are asteroids that are in so-called main asteroid belt between the orbits of Mars and Jupiter. And then the colorful dots are the objects that can come close to Earth. And by close, it means sometimes quite far, actually. But these are generally called near-Earth asteroids. The ones that stay always outside the orbit of Earth are colored in orange here. They're called AMERs. The ones that can come close to and cross paths with Earth, but they have their perihelia outside the orbit of Earth, so they have, sorry, their aphelia outside the orbit of Earth are colored in yellow, and they are called Apollos. Then we have Athens, which can again cross paths with Earth, but they have their perihelia inside the orbit of Earth. And then there are a few objects that we know of that have orbits entirely within the Earth's orbits. They're called Asteroids. And what we think we have found recently called Vatires are objects that are entirely within the orbit of Venus. So there's a lot of things happening here. The thing is, near-Earth asteroids, as we see them now, are on pretty unstable orbits in terms of the timescale of the solar system creation. So they couldn't have formed there. Where they did form, they formed in the asteroid belt, and then they were moved by various forces to the vicinity of Earth. The big move was the migration of young Jupiter, which just swept a whole suite of them towards Earth. And also migration of combined with migration of young Saturn. After that, and in more recent history, and we can still see new asteroids coming from the main belt towards Earth, towards the space which the near-Earth asteroids occupy, are pushed by different kind of forces. And one of the most likely causes of that migration is the sunlight. So what I show here is a picture from Bill Botkey's paper. about the Yarkowski effect, which is called Yarkowski to honor the Polish engineer that worked in construction of the Trans-Siberian train. And he had this idea that bodies traveling through the solar system are infused with ether, which people thought was a thing back then. And ether comes into pores of planets and fills them. And then as the ether is heated by the sun, it expands pretty much like steel in the railway tracks expands with the heat. And it gets expelled from the planet, creating a push, a small propulsion in the direction opposite to this ether being projected. We now know it's nothing to do with ether. It's just enough to have the solar radiation absorbed by a body and then re-radiated to create that little push. And it's very, very tiny, but it's always there. And it can cause very serious systematic effects in terms of Yarkowski effect. When the body rotates, one side gets heated up, and then as that heated up side moves away from the sun, it starts re-radiating the heat, and that heat creates a little push that can cause the orbit to either expand or shrink. And as the orbits expand or shrink, they land in special zones in the main asteroid belt that are in resonant motion with Jupiter or Saturn, which means they get a regular kick from gravity of either Jupiter or Saturn, which destabilizes orbit and can push the bodies from main belt to the inner solar system. And that's not when the solar radiation effects end. So in this, again, amazingly complex figure, which I should never be showing to anyone ever, we can see what we call two things. We can see the Yarkowski effect shown with the red arrows. So we can see which way the force pushes the object and which way the radiation gets emitted from the body. And the green arrows show what we call the Yorp effect. Now, the Yorp effect is a similar thing to Yarkowski, but it has to do with asymmetry of a body. So as a small asteroid gets irradiated by the sun, it gets heated up, but the surface re-emits that radiation not evenly in all directions, but depending on what the exact shape of the asteroid is, it can re-radiate more in one direction and less in the other, creating a small torque. And that small torque, again, very tiny, but it's always there. So it can change the rate at which the asteroid rotates, spinning it up quite quickly, or it can tilt the rotational axis of the small bodies. And the Yorp effect was one of the interests of my PhD work. So what shapes the orientation of the asteroid axis is mainly the Yorp effect. Of course, there are collisions that can happen between bodies, but they happen mostly in the main asteroid belt when we are already and they don't happen so often now. So nowadays, if we can see, if we observe some regularities in orientation of spin axis, they are more likely to be due to the Yorp effect than due to the collisions, because the collisions, while they're still happening, they're not happening all that often. And one of the first direct evidences of the Yorp effect actually acting in nature was this discovery that bodies in an asteroid family have only two preferred orientations of their spin axis relative to the ecliptic. And this was because Yorp was regularly tilting one way or the other depending on what the exact symmetry of the shape was, it could push them either to high or low inclinations. So this is the Yorp effect. And Yorp effect also has influence on the asteroid morphology. So what I study is asteroid shapes. And what Yorp can do is can spin up the objects. And now asteroids are made up of loosely bound piles of rock. And as those piles of rock get spun up and they rotate, they change their shapes. So material from the polar regions of the body can migrate towards the equator, creating what we call an equatorial budge. So this is the images of an actual 3D shape model developed from radar observations of asteroid Moshab. And here in the lower right, it's a numerical simulation of how this process of spinning up the asteroid and changing the shape works. And we can see that the shape is strikingly similar to what we actually observe with this asteroid. And this shape is actually quite popular among the near-Earth asteroids. So here are two pictures from two recent spacecraft missions from, sorry, three pictures from two spacecraft missions to two near-Earth asteroids. They are asteroid Ryugu, which was visited by Hayabusa 2 mission organized by the Japanese space agency JAXA, and asteroid Bennu, which was visited or is being visited by OSIRIS-REx mission organized by NASA. Those two missions have very similar goals. They're both there to collect samples from surfaces of those asteroids and bring those samples back to Earth. And by sheer chance, both of those asteroids look almost exactly the same. They do differ in composition, but still they look almost exactly the same. And we are quite convinced that this shape is because the asteroid was deformed due to quite quick rotation. So there's asteroid Ryugu, and there's asteroid Ryugu with the shadow of Hayabusa above it on its surface. And this is image of the site where Hayabusa shot a projectile into the surface of Ryugu before collecting the sample. So Hayabusa has already collected its sample last year, and it's on its way back to Earth. OSIRIS-REx is due to collect a sample with a robotic arm later this year, and then it's going to be coming back to Earth as well. And another thing that can happen when the asteroid is spun up quite quickly is it can shed mass. So the stones on the surface of the object are quite loosely bound, and we can observe sometimes them escaping from the surface. In the case of Bennu, which is shown here, it's not so sure that it is because of the fast rotation. There might be some other forces, maybe just solar radiation, lifting rocks off the surface or things like this. But in many cases, we can see that the fast rotation is spinning, the asteroid is spun up to the point where the rotation actually does lift the material of the surface. And we can see evidence of that because a lot of those asteroids that are shaped like this have little moons orbiting around them. Another thing that Yorp can cause, and another type of morphology that we observe among asteroids, and this is again an awfully complex and unnecessarily complex graph showing what can happen to asteroid after it's spun up quickly. So the morphology that it can lead to is called contact binaries. So as the asteroid is spun up, it can be elongated, and then as it gets elongated, it eventually breaks up into two parts. Those two parts then enter into a synchronous mutual orbit, and after a while, they gently collapse into each other, creating a contact binary asteroid. So this was proposed 9 years ago. We now know that there is more than one way to create a contact binary. And we can see quite a lot of them as well. About 30% of asteroids that we see, the near of asteroids that we can model with precise shape models, have this kind of shape. And another 20 to 30% are those contact binaries. And here in the lower left, there are 3 examples of such asteroid. One is observed with spacecraft. The first Hayabusa mission visited asteroid Itokawa, and this is the shape model from spacecraft. And then those 2 asteroids were observed with planetary radar from Earth. And this asteroid HW1 and asteroid JV6, which I worked on during my time at Kent. So one scenario of formation for asteroid binaries is that they are formed separately. So they are the 2 components that we see, that we can visually assess look like different components, are actually 2 separate bodies, and they formed independent of each other, probably quite close to each other, but they coalesced, they formed, and then they gently collided onto each other to form a contact binary. It's shown here on an example of not a near-Earth asteroid, but asteroid Arrokoth, which is quite far in the solar system. It's one of the trans-Neptunian objects. But the mechanism seems to be similar. Another way to form those elongated contact binary shapes is just by spinning them up. So on the left here, there are 5 examples of 5 different simulations of asteroids that have a weaker core and a strongly bound mantle. And as the asteroid gets spun up, there appears to form a hole in the mantle that leads later to the formation of the object. And depending on the ratio of the core to the mantle, that deformation can go different ways. And then with this very specific ratio of that weak core to strong mantle, we can see in the simulations that there is a massive dent created in the mantle that then grows, and as the asteroid gets elongated, it forms this region that looks very much like the neck region in the contact binary asteroids. So in this scenario, the contact binary asteroids are not the result of 2 bodies colliding onto each other, but they are rather a result of a single body just being elongated and stretched by the quick rotation. And one final scenario is the contact binary as being formed by coalescing fragments from a recent breakup. So the big body that gave source to the material that we can see in the contact binary asteroid is broken up by a catastrophic collision, and there is lots of fragments flying. And as those fragments start to self-gravitate, they just spontaneously, immediately create this shape. So, well, immediately, 300 minutes, 5 hours after the collision, we already see the contact binary. So rather than the fragments coalescing into 2 bodies that then gently merge over thousands of years, this is actually just after the collision, we immediately see those shapes in the numerical simulations. So for contact binaries alone, there's 3 different scenarios, who knows, maybe even more, of how they could have formed. Which is why I'm really interested in asteroid morphology. And I want to link these morphological features with those possible formation scenarios, because the formation scenarios also link to what the asteroid looks like inside. So what's the structure of the asteroid is inside, which can be very important if we're planning spacecraft mission or if we're planning deflection for planetary defense reasons. So we're looking at that. And how we're looking at asteroid shapes. I'm going to now talk about how we collect the data. So this is me in La Silla Observatory in Chile. This is ESO's oldest, European Southern Observatory's oldest site in Chile. You are perhaps more familiar with the VLT and the Paranal Observatory, the very large telescopes that are a few hundred kilometers further north from La Silla. And very close to the VLT site, the European Space Observatory is now building the extremely large telescope, ELT. You can actually see it from one mountain to the other. You can see the building site. If you're at Paranal, you can see the other observatory. But we use those telescopes that are on the ground to look at near-Earth asteroids. Of course, ideally, we would just send spacecraft to all of them. The problem is this is a very, very expensive solution. So far, out of all of those asteroids that are depicted here, we can see both near-Earth and main belt asteroids like Ceres and Vesta up here. We can see Bennu and Ryugu and Itokawa. So among all of those asteroids that have been even briefly visited by spacecraft, only 12 of them are near-Earth asteroids. So it's not a very efficient way of investigating near-Earth asteroids. And we want, when there are thousands and thousands of them, we want to know as much as possible on them without ruining the world's budgets on sending spacecraft to every single one. So we need to use the instruments that are on Earth and that are perfectly capable of very good characterization of asteroids, especially those that are close enough to take a good look at them. So first and foremost, for my PhD at least, was to study using asteroid light curves. And those observations were done using optical telescopes. Examples of those are the NTT, which is the New Technology Telescope, again, very creative name from ESO, and the ESO 2.2 meter telescope, both in La Silla. There's a few other telescopes that we used around the world as well. So a typical observing run at such telescope looks like this. You sit in front of a computer in a steering room. Actually, when you look at the site here, that's the entity here. This picture was taken from a different telescope. And between the buildings, you can see the roof of a hotel in which the astronomers sleep. And behind the hotel, down the hill, even further down the hill, there is more or less at this level as those buildings here, there is the steering room in which you actually sit and observe. So you are quite removed from your actual instrument. And you sit in front of a computer and you get your images. So this is a mosaic of 3 images of an asteroid that I observed. So you can see the asteroid moving across the frame. So if you stack the images using the position of the stars, you get to see how the asteroid moves. If you stack the images on the position of the asteroid, you can see that the stellar background has changed. I use both, and I compare the brightness of the asteroid in the asteroid stacked image with the brightness of the star in the star stacked images, and I calculate the relative change of brightness of the asteroid over time, which is called the asteroid light curve. So light curve is basically an illustration of how a brightness of a source changes with time. Another source of information about asteroids is the planetary radar. Now, the planetary radar is quite a unique way of observing doing any astronomical observations, because unlike the optical observations where you just gather photons that come at you, you actually send the photons towards your target. So there is a powerful transmitter here in this little dome here that sends the signal that gets reflected from the telescope dish. It goes up to the target, it gets reflected from the asteroid, comes back and gets received by the telescope. There are currently only 2 active planetary radar observatories in the world. One of them is the Arecibo telescope in Puerto Rico. It's 300-meter diameter single dish telescope. The telescope, the primary mirror doesn't move. The secondary mirror moves on an azimuth arm that is hung from a platform supported by 3 pillars above, about 150 meters above the dish. And this part can move. It can rotate and it can move along the azimuth arm to point the telescope at the sky. It has very limited sky movement. A fully steerable antenna that is part of the Deep Space Network in California, the Goldstone Solar System radar on DSS-14 is the other instrument. So there's only 2 instruments equipped in planetary radar, and at the moment none of them is working because the DSS transmitter is being fixed, and the Arecibo got broken just a few days ago. So what happened was one of the steel cables that hold the platform up, there's quite a few of them. So there's a few main cables. I think there's like 3 main cables, and additionally each point of the triangle, so each pylon additionally has 2 auxiliary cables, and one of those auxiliary cables on one of the pylons has snapped, and it has hit the dish, creating a 30-meter hole in the surface of the telescope. So you can see, I don't know if you can see it in the live feed, but there is the steel line dangling from the platform that is above the telescope that needs to be removed before any operations can be resumed, and then the structural integrity of the whole thing has to be checked. So it might be a few months for us without active planetary radar. Hopefully Goldstone gets fixed soon. It was supposed to be fixed sometimes in August, so hopefully they can resume operations soon and we're still going to be safe and we can still observe asteroids. But when it's functioning, this is how the observations with Arecibo look like. So you have the instrument, the telescope, and then very close, you can see the telescope actually from the control room. You have a control room in which you receive the signal from the telescope, and you can see after processing the data, you can see the images created with the radar. And on the right here is a series of images of an asteroid that I was observing and modeling. The planetary radar observations are quite different to optical images. So in optical images, when we look at something, the image that we capture is a 2D image similar to what we would see with our own eyes. So we can see 2 dimensions. We can see up from down and left from right, or north from south and east from west in an astronomical image. If you looked at the images during the remote observing sessions, you can see that they are calibrated. So you can see there is the right ascension dimension and the declination dimension in those images. In radar images, we also have 2 dimensions. but it's a bit different. So what we see is on one axis is the delay of the signal. So the distance, the delay is linked to the distance the light has to travel from the telescope and back, from the telescope to the object and back to the observer. So we can see when we receive the radiation back after emitting it from the telescope, the signal comes at different delays because it had to travel further or shorter distances depending on where on the asteroid the light was reflected. So one of the dimensions is the distance. The other dimension is called Doppler. So the images are called delay Doppler images. And the Doppler is linked to the Doppler effect, which comes from the Doppler shift of the frequency of the emitted signal. So we emit a radio wave that has a very precisely set frequency. It's 8,310 kilohertz or megahertz in Arecibo. Okay, I'm stupid, I don't remember now. Anyway, there's a very precise frequency at which we send the radio signal, and that gets shifted, blue shifted or red shifted, depending on how quickly a part of asteroid moves towards us or away from us. So there's a small illustration of how that works. So you can see the asteroid 1996 HW1 rotating. This is the image we would see if we just had a camera pointed at the asteroid good enough that we could resolve the surface details. So as it rotates, this is up and down, left and right. So the central image is what we would see in the sky if we had instrument good enough. Now the image here in the upper left is the radar image that we would get if we were observing that asteroid at that moment. So we can see as it rotates, the parts that are closer to us appear lower on the y-axis, and the parts that are further from us appear higher, so further away from the observer. So this axis here would be the delay. Now the horizontal axis is the Doppler shift. So you can see that parts of the asteroid that are moving towards us are on the left side of the image. The parts of asteroid that are moving away from us are on the right side of the image. So the actual radar Doppler delay image of the asteroid is like as if we were looking a little bit as if we were looking at the asteroid from the top. So the image is created not perpendicular to our line of sight as we are used to with our little optical detectors in our eyes, but it's rather created parallel to our line of sight, which is a bit much to get your head around first time around. So don't worry about it too much. Another illustration is how the radar, here is how the radar image changes with the axial tilt of the object. So depending on how the asteroid is oriented towards us when it rotates. This is just snapshot at some point in the rotation, what we would see. So as we observe the asteroid more pole on, so it would rotate like this, the bandwidth, so the difference in the Doppler dimension gets narrower because there is smaller velocity difference between different parts of asteroid. If we look almost directly at its equator, which we will see in a moment, so right now, the image, the radar image gets wider. So there is a massive velocity difference between different parts of the asteroid, so we can see a wider image. So this is how the asteroid radar observations work. And this is some examples of asteroids that we can image with the planetary radar. So we can see the weirdest shapes. We can see the contact binary shapes like the asteroid that I showed you earlier. We can see binary asteroid. So this is an asteroid with a small moon close to it, so you can see both the asteroid and the moon, and actually most of the asteroid binaries are discovered like this, or multiple systems. So there are systems with up to 3 little moons discovered by planetary radar like this. And we can see some weird angular shapes that we are not really sure how they look like, with like asteroid BQ6 here. So they look a bit like Dungeons and Dragons dice from afar. So there's all sorts of things that we can learn about asteroid morphology from radar observations. And to finish off my talk, I'm going to talk a little bit about how do we actually recover the shape information from asteroid observations, starting with the light curve inversion, so with the optical light curves that we collect with optical telescopes. So those 2 images here come from the observations that I performed with a robotic telescope in the Canary Islands. And this is a stack of 400 frames, just to show how the asteroid moves through the star field. So this image here was stacked to keep the stars in the same place, and the asteroid is visible here as this very faint smudge moving across the star field. And this image is the stack of the same 400 frames, but this time I kept the asteroid in the same position and I let the stars drift away. So you can see the asteroid image quite sharp, and you can see the stars zooming by. So what I do, rather than stacking images, rather than stacking all of the images, I normally look at it frame by frame, and I look at the brightness of the asteroid relative to the brightness of the stars in the background. And that's how I create this so-called asteroid light curve, so the changes of brightness of asteroid in time. And this is a collection of light curves for one of my asteroids collected over 22 years, 32 years, a lot of years. Sorry, I'm really bad at maths, 22 years. So there is light curves from 1999 all the way to 2011 and even further. That didn't fit in this picture, but you can see the horizontal axis is the rotational phase of the asteroid. So as the asteroid rotates, it can reflect the light with larger or smaller surfaces. And if it reflects light with a larger surface, more light gets to us, so we can see a brightening in the light curve. If it rotates so that we can see the narrow end, we will see less light, so we can see the fainter parts or a minima in the light curve. And as we collect those light curves over the years from different orientations, we can start thinking about reconstructing the 3D shape of the object. The first step to do is assess the periodicity of those changes. So we'll look at the rotational period of the object. The easiest way to do that is to just try different possible periods and see if it fits. And this is basically what we do. So for this target, I tried periods between 2.5 and 4 hours. And for each period, I tried to see if you can match the points and if they create. So this is here in black and red, there is points from the consecutive different nights. And you can see that with a period around 2.7 hours, they overlap quite nicely, and they overlap quite nicely over the whole period of 20-something years that this asteroid was observed. After I have the initial period, I go to determine the rotational axis. Now, because of the conservation of momentum, the orientation of the spin axis of the asteroid is constant relative to the ecliptic. So, sorry, and constant relative to the orbital plane of the object. So what we can see here in a plot that should be familiar to those of you who did a little bit of spherical astronomy in during the camps. So we can see the plane of the ecliptic, and the green line is the orbital plane of the target. And the purple arrow here is the spin state orientation, the orientation of the rotational axis of the object. And the angle between the ecliptic, so there you can measure an angle, an ecliptic longitude and latitude of this spin axis. And that gives you information about the location of this axis that is essentially fixed in the timeline of your observations. As I said before, your perfect can change that, but it changes it over tens of thousands of years. So over the few tens of years that we can possibly observe an asteroid, that's not a big problem. So we can still assume that it's fixed in that time frame. But it's affecting the way, the shape of the light curves. And to disengage that effect from the effect of the actual shape of the light curve, the actual shape of the object has on the shape of the changes in brightness, we treat the spin axis orientation as a fixed parameter in the fit. So to put it more simply, I divide the sky, the plane of sky, into a grid of points in ecliptic longitude and ecliptic latitude. And for each of those points, similar to what I did for each of the periods earlier, I check for which orientation of the spin axis I am able to best reproduce the light curves if I manipulate the shape a little bit. So at each point of the possible pole position, I optimize the shape so that it gives the best fit to the light curves. And I compare those across the sky to see which point gives me the bestest fit of my light curves observations to my synthetic light curves that could be produced by my shape. And I get a three-dimensional shape of the object. Now, the problem with the convex light curve inversion is in the first word, which is convex. So we can reproduce shapes of a lot of asteroids quite effectively because light curve observations are quite easy to gather. The problem is the method of retrieving the shape information from the light curve observation is not perfect. And it cannot tell you everything about the shape. It can essentially give you the idea of what the ratios of different reflecting surfaces are over time. As you combine it from different time frames, you get like a gift-wrapped image of the object. So you get an idea of what the proportions are from different angles, but you don't get information about the details that are often important, which is details like this very clear neck region in this. This is the same asteroid, but modeled with different methods. So you don't get that. You don't get the neck regions. You don't get the craters. You don't get the ridges from convex inversion. In order to get all of those details, we need to look at radar observations, and this is the other ground-based method that I use. So here in the middle, you can see the real observation, the Doppler delay observations of asteroid JV6. So again, horizontal axis is the Doppler shift or the velocity of different parts of the surface. The vertical axis is the delay of the signal, so how far the signal traveled before it was bounced back towards the observatory. So this is the delay or the distance to different parts of the surface. You can see how it changes with time. And Here on the left is the shape model that it developed using light curves alone. And while this model was quite good at reproducing the light curves, you can quite clearly see, especially like in this image here or in this image here, that it's not able to reproduce this neck thing of the contact binary, of the apparently contact binary asteroid. And here is the shape model developed using the radar data and the synthetic echo created from this. And you can see it corresponds to the actual observations much better. Now, modeling radar data is a stupidly complicated process that takes ages, whoever did any of it. So first of all, you need to process all of your, data. So you need to look at every single frame that you collected for that asteroid. You need to identify where the signal is, more or less. And you need to configure an input file for your shape modeling procedure that will then develop that shape from your data. Then you have to construct a simplified shape. And then you combine the data with the simplified shape and a grid of possible pole solutions, similarly to the convex inversion, to get the idea of where to best put the rotational axis so that the object is, the radar echoes are best reproduced. And this can take a week or a few weeks to perfect. And then after you have that, you have to optimize the fine details of the surface to reproduce all of the little craters and little bumps and crevices that you see in the images so that they would be reflected in the shape model. And that requires you revisiting the model many, many times, tweaking the parameters, and this can take months. So for me, from gathering the first data in 2015 to publication last year, it was 4 years for this object to be finally published. So it's a lengthy process. You can try using the convex inversion model. This is the convex light curve inversion model that was developed using the optical light curves only as a starting point, but the problem is the procedure, the program that is used to develop those shape models is not very intelligent. I mean, programs are only as intelligent as the people who use them. And if you're silly enough to use a shape model that is too far from your solution, you might get weird artifacts popping up. So this is my asteroid, this is my shape model that I use as a starting point, and this is what the program came up with, and it looks a bit more like a hedgehog than an asteroid. So a better starting point was a contact binary that I manually set up to be 2 ellipsoids that are slightly overlapping, because I thought this is what I see in the radar images. And I used this to check the whole celestial sphere. You can see the celestial sphere here from east, west, north, and south. And I located my pole, the darker the color, the better the solution, to be somewhere close to the south pole of the celestial sphere in ecliptic coordinates. And once I knew that, I could go a step further and I could look at the fine details in the surface. And this is the final shape model that I came up with for this asteroid. So after many years, I was able to publish my results. But this is what the process involves. So you need to have a very good starting point in order to develop the radar shape models. So there is pros and cons of both methods of ground-based characterization of near asteroids. The light curve method is good because it's very accessible. A lot of asteroids can be observed using light curves, and you can produce the shape models quite quickly because there's only one solution ever. With radar shape models, the process is lengthy, but the outcome is much closer to what the actual asteroid looks like. And we have now ground truth for radar shape models, because a few of the asteroids that were modeled using radar were also visited by spacecraft. So we had a model of Bennu, for example, before the OSIRIS-REx mission arrived, and it's really, really close to what the real asteroid looks like. So this technique is very, very good, but it's also very involved, and it requires a lot of input from the user. So this is basically the end of my talk.